unveiling the dynamics of Mediterranean cyclones, impacts, classification, and future trends. The Mediterranean basin is a geomorphologically complex region that combines multiple climate types and is a well-known area of frequent cyclone formation. Cyclones play a key role in synoptic scale variability and are connected to extreme weather events that result in large-scale property damages and human casualties. Therefore, the study of cyclones and their characteristics is a vital subject involving the agricultural, socioeconomic, tourism, and health regimes of the Mediterranean. Mediterranean cyclones govern extreme weather events across the Euro-African region. Mediterranean cyclones are the primary source of extreme precipitation, winds, temperatures, and dust events. As such, Mediterranean cyclones pose significant threats to society and challenges to weather and climate predictions. The impact of cyclone underprediction on the heavily populated Mediterranean coast and further inland is tremendous. Flood and wind damage may result in the loss of homes and even lives, while better weather predictions may allow for better warnings and preparations to reduce costs significantly. On climate scales, low confidence in the response of Mediterranean cyclones to a changing climate may lead to an underestimation of the severity of the impact of global warming on the Mediterranean and to inadequate infrastructure planning. The recent increase in extreme weather events in the Mediterranean region, including droughts, windstorms, and hot spells, are all linked to changes in Mediterranean cyclone behavior. Despite many studies addressing Mediterranean cyclones in recent decades, their correct simulation and prediction remain a significant challenge and may be attributed to the large variability among these cyclones. There are many algorithms and methodologies that have been used in previous studies to study cyclones, including identifying cyclone centers and the associated tracks. The meteorological parameters used in such a process can also vary. The most used parameter in cyclone detection and tracking studies is mean sea level pressure. Past classifications of Mediterranean cyclones are primarily based on geographical and/or seasonal separations. However, it is very important to focus on cyclone genesis and deepening mechanisms. A variety of processes combine to govern Mediterranean cyclone genesis and evolution, including adiabatic and diabatic processes, topographic influences, land-sea contrasts, and local temperature anomalies.
In the Mediterranean case, the first-order connection is between geography and seasonality, but from a dynamical standpoint, similar cyclones may occur in different regions or seasons, while substantially different cyclones may appear at the same location and season. Ideally, the dominant deepening process determines the course of evolution that a specific cyclone will take. For instance, an alpine lee cyclone or a Genoa low, which is very frequent in the Mediterranean, deepen much faster at their initial stages compared to cyclones forming away from topography. However, the lee cyclones may then undertake an unusual evolution path due to their large-scale forcing or by warm surface temperature anomalies that favor a wind-induced surface heat exchange mechanism and then a tropical-like cyclone growth. So therefore, our objective was to characterize or classify Mediterranean cyclones in a simple way that addresses the theorized cyclone driving mechanism. Ultimately, such a classification will serve to enhance the ability to predict features such as cyclone duration, propagation, precipitation, and more, which are nowadays harder to predict.
Because each process leaves a distinct signature on the potential vorticity field, the potential vorticity approach has been used to distinguish among different types of Mediterranean cyclones. In this study, a cyclone tracking algorithm is used to detect 3,190 Mediterranean cyclone tracks in ECMWF ERA5 from 1979 to 2020. Cyclone-centered upper-level isentropic potential vorticity structures in the peak time of each cyclone track are classified using the self-organizing map, or SOM. The SOM analysis reveals 9 classes of Mediterranean cyclones, with distinct Rossby wave-breaking patterns as discernible in corresponding potential vorticity structures.
From the large-scale perspective, the birth, evolution, and decay of the cyclone are usually linked to that of the PV streamer it interacts with. These PV streamers denote the penetration of cold air from the north into the Mediterranean, where it mixes with the warm, humid air masses and grows into a cyclone. The cyclone can then influence the upper-level PV structure, and so these PV streamers may develop in many ways and are challenging to predict. However, 2 paradigms of anticyclonic and cyclonic Rossby wave life cycles are known. Cyclonic life cycle, or life cycle 2, is used to describe a life cycle where the wave breaks inwards, reflecting the wave energy poleward back to its source. In the northern hemisphere, it means that the PV streamer is itself rotating counterclockwise cyclonically, wrapping itself around the cyclone and intensifying it. Anticyclonic wave breaking, or life cycle 1, occurs when the opposite is true. The PV streamer rotates anticyclonically, tilting the wave into a destructive easterly tilt with height. This formation tends to dissipate the wave energy faster, leading to a weak cyclone and dominant anticyclone. Both life cycles may or may not generate a cutoff flow, which is another category we can look at. On the other edge of the scale, there are also heat lows. They are mostly a bottom-top phenomenon, where local temperature anomalies sustain the cyclone and upper-level forcing is weak. Other notable mechanisms are daughter cyclones, which are secondary cyclones forming adjacently to synoptic scale ones, and the wind-induced surface heat exchange WICHI, which I mentioned before, which involves diabatic heat release. In addition to all of these, topography plays a crucial role, especially in triggering extreme deepening rates in the initial stages of cyclogenesis.
Though classified by upper-level potential vorticity structures, each class shows distinct flow structures across the tropospheric column. Unique cyclone life cycle characteristics, associated hazards such as precipitation, winds, and temperature anomalies, and long-term trends, as well as synoptic, thermal, dynamical, seasonal, and geographical features of each cyclone class indicate dominant processes in their evolution. Among others, the classification reveals the importance of topographically induced Rossby wave breaking to the generation of the most extreme Mediterranean cyclones. These results enhance our understanding of Mediterranean cyclone predictability by linking the large-scale Rossby wave formations and life cycles to coherent classes of under-predicted cyclone aspects. One feature known to modify Mediterranean cyclogenesis is topography. Climatological studies of Mediterranean cyclones reveal the uneven distribution of cyclones across the basin, with primary cyclogenesis hotspots strongly linked to topography. For this reason, most classifications of Mediterranean cyclones focus on geographical and seasonal features, where Genoa cyclones, North African or Sharav lows, and Cyprus lows are the dominant modes of Mediterranean cyclones. Genoa cyclones form in the lee of the Alps and dominate the winter season. These lee cyclones tend to travel east toward the Balkans, Greece, or Turkey. The Sharav lows are known to appear mostly during summer and spring and tend to initiate in the lee of the Atlas. Cyprus lows frequently occur in the winter and autumn seasons, providing the majority of the precipitation events in the Middle East. Other recognized climatological hotspots for cyclogenesis include the Adriatic, Aegean, and Black Seas, and the Iberian Peninsula.
Based on upper-level PV structures, from a cyclone-centered perspective, we derive 9 cyclone types, or clusters. Each cluster is representative of a different dominant deepening process. Cluster 1, Stage A lee cyclone. These cyclones peak while still locked in their initial rapid deepening phase. They are the coldest and deliver strong winds and dry conditions. Cluster 2 is anticyclonic and cyclonic wave-breaking cyclones. These are the windiest cyclones due to their constructive interaction with topography. These relatively static cyclones are linked to compound extreme events. Long wave cutoff flows is cluster 3. These are large chunks of air separated from the main PV reservoir, tend to form in the lee of the Atlas but may also appear in the Black Sea or elsewhere. Cluster 4 represents the second stage of the lee cyclone deepening, which is stage B. These cyclones are more similar to freely traveling waves over the oceans with a strong frontal structure. Cluster 5 represents anti-cyclonic wave-breaking cyclones. These are in line with theory as they tend to be weaker and shorter. Cluster 6 represents Sharav lows, which are dry, warm cyclones mostly over North Africa, although they recently started appearing over Europe. Cluster 7 are the daughter cyclones, which are shown to mostly form over the warm sector of the synoptic cyclone. They are rapidly deepening and fast-traveling cyclones. On cluster 8, we have the cyclonic wave-breaking cyclones. They are intense and more static. These cyclones are the stormiest in the transition seasons. And in cluster 9, we have short-wave cutoff flows. They form under rich conditions and they generate warm anomalies even in summer.
Mediterranean cyclones are expected to decrease in frequency across the northern Mediterranean, along with an expected poleward shift of the Atlantic storm track, though their intensity may increase in some cases as the Mediterranean becomes warmer and tropical-like cyclones emerge. To improve the understanding of present and future extreme weather events in the Mediterranean, it is crucial to better understand their mediators, Mediterranean cyclones. Changes in Mediterranean cyclone intensity, frequency, duration, propagation, or extent all have implications for future climate response.
So one such highlight would be the detection of opposing long-term trends between differently driven cyclones. Specifically, we see a decrease in winter lee cyclones, clusters 1 and 4, and an increase in heat lows. This is important because lee cyclones provide most of seasonal precipitation in Western and Central Europe, whilst cluster 6 and 9 are associated with extremely warm and dry events. We believe these trends reflect a worrying response of Mediterranean cyclones to climate change that was not considered before. From a theoretical standpoint, revealing the double wave-breaking pattern, which is cluster 2 representing anticyclonic combined with cyclonic wave-breaking, has an important value. It challenges the idealized life cycle 1 paradigm by showing that it can also develop into a life cycle 2 at later stages. This combined life cycle demonstrates the synergistic relationship between PV advection and topography, but it also involves strong evaporation precipitation processes, producing the most intense Mediterranean cyclones. Future changes in the frequency of such life cycles, perhaps due to increased sea surface temperatures, may provide yet another feedback to climate change.